this problem.
Okay.
All right, so those two lines are parallel. And they want you to find the perimeter of HJF, which means finding the lengths of everything.
Mm-hmm.
So we need to solve for X, we need to solve for Y, and that's it. Okay. So, what do we know? Is GK a midpoint line?
Yes.
How do we know that?
Because they're parallel.
Doesn't make it a midpoint line. In other words, if I were to draw a line like that, that's parallel also. Right?
Mm-hmm.
So parallel doesn't make it a midpoint. We're used to seeing it as a midpoint, so we're tempted to say that x plus 3 has to equal 9, but they don't say it's a midpoint. Unless I'm missing something, they only say that it's parallel.
Mm-hmm.
So, what can we do with that? What does it say about that number and that number versus that number and that number? Those ratios need to be the same. Okay? In other words, 9 is...
9 over...
Go ahead.
9 over 4 equals x plus 3 over x minus 2?
You can actually do it many ways. You can do it that way. 9 over 4 has to equal x plus 3 over x minus 2. I can solve that for x.
Mm-hmm.
I can also say 9 over x plus 3 has to equal 4 over x minus 2. Notice you get the same thing when you cross multiply both of these.
Mm-hmm.
So it's okay. We don't need to know all the ways we can do it. So I don't need to know that way. So help me solve that.
9x minus 18 equals 4x plus 12.
Keep going.
And then you add 18 to 12.
Okay.
And you get 30.
Okay.
And then it would be 9x equals 4x plus 30. Subtract the 4x. 5x equals 30. So x equals 6.
Okay. So now we know a lot.
Mm-hmm.
We know x. Now, how do we figure out y?
I want to say that it's 14 because it's just double 7, but we don't know if it's a...
Well, and in fact, if that is not a midpoint, then it is not 14.
Yeah.
The way that's a midpoint is if it's 14. However, think similar triangles. Which two triangles are similar?
HJF is similar to GKF.
Okay. So corresponding sides of corresponding, well, sorry, that's congruent triangles. However, with similar triangles, ratios are all the same.
Mm-hmm.
So give me an equation that has the ratio y in it that has to be true.
9
Okay, let's do it. It's a little tricky. So let's do it like this. I'm going to take that triangle out, and I'm going to draw it over here. And this is a little technique that I use every now and then when it's really valuable. Now, what do I know about this triangle?
The triangle.
It's similar to the blue triangle. So, give me some equations.
9/18 equals 4/8.
Also equals, we're trying to solve for y. We got to get y in there. In other words, what you're doing is trying to figure out that triangle that I just circled is similar to the blue triangle, which means the ratios of the sides. So if I say 9, what's the length of that blue side? It's x plus 12. Has to equal what?
Equals 7/y.
Right. In other words, 7 is the base of the smaller triangle. It's that one. Y is the base of the bigger triangle. So that ratio has to be the same ratio as all the others. The really easy mistake to make here is to say 9/x plus 3. Okay? Because it almost looks like you should be able to do that. 9 is to x plus 3 as 7 is to y. But it isn't. 9 is to the full side, which is x plus 12. So don't fall into that trap. Okay, so turned out this was a midpoint line all along, wasn't it?
Yeah.
But they never told us it was, so we really couldn't use that information. We still haven't solved for y, but we know x is 6, so we have 1/2 equals 7/y, so y indeed is 14.
Yes.
That's the only problem on this page, right?
Yes.
Okay, let me go to the next one. Okay. Is there a 1 on here, or is this it? 2 through 10?
It's 2 through 10, and I don't know what number 2 is asking.
I'm not sure I do either. Hold on a second. My TV, I forgot to turn it off. No, I didn't. Just 1 second. All right. I thought I had turned it off, and I hadn't. All right, let's look at number 2. Find the fourth proportional to 4, 6, and 8. I have no idea what that means. I suspect it might be related to question 1. What does question 1 say?
Identify the means and extremes in the proportion A/B equals C/D.
Okay. Let's do number 3, and we'll get a feel for this a little better. When they say the mean between 5 and 20, what they mean is there is some number that's the same in that denominator as it is in that numerator, that represents the mean between 5 and 20.
Mm-hmm.
Can you figure out what it is? Can you solve that equation?
100 equals x squared, so x equals 10.
Okay. Actually, in this case, x could be plus 10 or minus 10.
Oh yeah, because it's squared.
Yeah, well, no, it's if I use minus 10, that works. In other words, the equation is still valid, whether you use plus 10 or minus 10. And that's what's important. So x could definitely be plus 10 or minus 10. Now, I'm a little curious about the plurality of that. Oh, there were two of them, plus and minus 10.
Yeah.
All right, so your first question was A over B equals C over D.
Yes.
So AD equals BC. And what was the question again?
The means and extremes. So the means would be A and D, and the extremes would be A and D, and the means would be B and C.
Okay, that's what they mean. Find the fourth proportional to 4, 6, and 8. What could they possibly mean here?
Maybe it's 4 over 6 equals 8 over x.
I honestly don't know. What did you say? 4 over 6 equals 8 over x. Make x 12.
Mm-hmm.
Sounds like a reasonable answer. I have no idea what their terminology means here.
It's really confusing.
Yeah, it is. I don't know what he means. You might be absolutely right. I know what mean means. It means this number has to be the same as that number when you talk about a mean between two ratios. Well, when you talk about a geometric mean. Okay. So let's just go on. Let's do 4. Give me the equation.
The geometric means between 3 and 6.
Mm-hmm. Actually, this is important. I neglected to point that out. I think that this geometric means is the same as that mean. And the only reason it says mean proportional is because there were two of them. Let's see if there are two of them with this one. So what's the equation?
It'd be 3 over x equals x over 6.
Yeah. Which means x squared equals 18, which means x equals plus or minus the square root of 18. Simplify that. Remember the method. You got to find factors of 18, one of which is a perfect
So it could be 9 and 2, so 3 square root 2.
You got it. So I believe that's the answer.
Mm-hmm. I've never actually, they never went over what a geometric mean was actually, so
That's exactly what it is. It is what number is in the denominator of the first number and the numerator of the second number to make this an equation.
Okay.
That's exactly what it means. It's simple. I'm not sure why this doesn't say the same thing. Why number 3 doesn't say find the geometric means between 5 and 20. Because that's what we found. I'm not sure why it uses different terminology, to be honest.
Mm-hmm.
But I don't suspect that that is particularly important. I mean, it might be if you get a test question on it, but that's what usually is talked about is the geometric mean.
Mm-hmm.
What's the ratio of x to y? What do you have on one side of the equation when we're done?
X and Y.
Be specific. What does it have to say? What's that mean?
It means it has to do...
What's the ratio of X to Y? How do I write that?
X over Y.
That's it. So that's what has to be on one side of the equation. How do we take that equation and get an X over Y?
Is it just 9X over 4Y?
No, we'll start by trying to get that. So what's a good first thing to do?
Divide the Y by 4.
Well, let's divide both sides by Y.
Oh.
There's 9X over Y. Now how do I get rid of the 9?
Divide both sides by 9.
So we get X over Y equals 4/9. Okay. All right. Given that these two triangles are similar, and by their terminology, one hasn't been rotated. In other words, that one is the same as that angle. This angle is the same as E. And this angle is the same as F. Not always like that, because they could have been rotated. Their terminology would be different, though. They wouldn't say ABC is similar to DEF. They would say ABC is similar to FED. So that angle B would be similar or the same as angle F if one had been flipped. But they haven't. In other words, we know that, B is the second letter, E is the second letter, so those two angles are the similar angles. Okay. So I think I can erase all of that. It's as it appears. What's DF?
DF is 9.
Okay, give me the whole equation.
It would be 8 over 6 equals 12 over X, and then when you multiply it equals 9.
Let me give you just a little tip here. When you're setting up these ratios, they're one step easier to solve if the variable is in the numerator.
Oh, so go from small to big?
Yeah, so if we go, and I'll show you why exactly. To solve this, I only have to multiply by 12.
Mm-hmm.
To solve this, I got to cross multiply, and then I got to divide by 8. So this is one step, that's 2 steps. So when you have a choice, it isn't always going to be small to big. It's going to be wherever that variable is, which in this case is right there, you want that in the numerator. And that requires you in this particular problem to go from small to big, to have it in the numerator.
Mm-hmm.
Okay. So we get X equals, let's see, down here, if I multiply by that, and now I do 72 divided by 8, I get 9.
Mm-hmm.
And you had that already. Notice, I want to point this out repeatedly because I think it confuses some students. Let's say they had given us that. And now we want to solve for this. I'll call this Z. There are multiple ratios that can be set up. Give me one.
6, well, 6 to 8 equals 10 to X, equals X to 10.
Or in this case, Z to 10.
Yeah.
So that's one, where you're going this side to that side equals this side to that side. But it turns out on these problems, whenever you don't have to go that way. You can also say 6 is to 9. 6 is to 9 as z is, excuse me, let me start again. If that 9 is in there, and I call that z, then I know 6 is to z as 8 is to 10. Notice that in the first case, you did this corresponding side is to this corresponding side. But you can also go this corresponding side to that is the same as that to that. In other words, you can set up your ratios between the two triangles or within the triangle. Now, the fact that they didn't give us another dimension in the smaller triangle, we only had one way to do that. In other words, when we called that x, we had to say x is to 12 as 6 is to 8. I believe. No, we didn't. We could have gone x is to 6 as 12 is to 8. Could have also done that. Two actually completely different methods, but it's one that you should know these, because I can remember when I studied geometry, this was confusing for me. And I was constantly kind of getting a little mixed up as to which one you had to do. It turns out you can do either one. Either way works. And then once you solve for that, that's a piece of cake to solve. Let's see, what did x end up being? 9?
Yeah.
So the proportion appears to be 3 to 4. So what do we got? We got z is to 10 as 9 is to 12. And that's a little harder because now z ends up being 90 divided by 12, which is an improper fraction. It's not a whole number.
So it's 7.5.
Okay.
Or 7.5.
All right. All right. Number 7. Here, let me scroll up a little bit. That's as far as I'm scrolling, I guess.
Yeah, we only have to do number 7 and then skip to number 10.
Okay. So 7. Give me the ratio based on that information right there. There's a key terminology. That terminology is similarity ratio. Okay? That is the linear ratio between two shapes. And in other words, in this figure right here, the similarity ratio is 8 to 6, right?
Yeah.
Okay. Well, what's the similarity ratio in 7?
24 to 30.
Correct.
So then it reduces
from that to that. So this one's the bigger one. The A prime, B prime is the bigger one. It's got the bigger perimeter. So the A prime, B prime line has to be bigger than 6. So what's the ratio that I want to set up?
4 over 5 equals x over 6.
4 over 5 equals x over 6. X going to be smaller or bigger than 6?
Based
on this equation right there.
It's going to be a little bit smaller.
Is that correct?
Yeah.
No. A prime B prime has to be bigger than 6. The perimeter of this pentagon is 30. The perimeter of this pentagon is 24.
Yeah.
So that immediately tells you you've got one of these backwards. So 24 over 30 is equal to the little one, AB, over the big one, which gives us 24 over 30 equals, what is that, 6, AB?
Mm-hmm.
Over X, we'll call it.
Mm-hmm.
So you said this was 4/5. So we got 4x equals 30. X is again 7.5. Not x, but A prime, B prime. Okay? So that's an important mistake you made. I'm glad you made it, because it teaches you how to make sure you don't make those mistakes. That's a really, really easy mistake to make. And the only thing you have to focus on is make sure you're going from little to big in both cases, or big to little in both cases. Don't go from little to big in one case and big to little in another. Okay?
Mm-hmm.
So this is actually 6 over x. Yeah. That's why it comes out to be 7.5. Okay. And now number 10.
Yes.
Okay. These are like trig problems almost. There's the radio antenna. It's 100 feet tall. Cast it's 100 meters tall, excuse me. It casts a shadow. We'll pretend the sun is up here. The shadow is 80 meters long. So this is all shadow from that antenna. At the same time, a nearby telephone pole casts, well, here's the nearby telephone pole. It casts a 16-meter shadow. Find the height of the telephone pole.
Mm-hmm.
So basically, we have two similar triangles. Now, why are they similar? Because the sun, that angle is the same as that angle, as long as these two poles are vertical on the earth. Merely because the sun is some number of millions of miles away from the earth, and so according to these two objects, this antenna and this telephone pole, the sun is at the same angle. The sun is hitting them at the same angle. So this angle is the same as that angle. That angle, they're both right angles. That means this angle is the same. We have two similar triangles. Give me an equation to relate them. Sure, that's in the numerator.
Sure, that's in the numerator. So 16 over 80 equals k over.
Okay, let me stop you for just a moment. To make sure that's in the numerator, write it like that. Start off.
Okay. And
there is a difference, because you had to go to step 2 to figure out how to get h in the numerator, right?
Mm-hmm.
Whereas me, I'm just putting it in the numerator. Now I can relate it to either the 100 or the 16. Take your poison.
Mm-hmm.
Pick your poison. What goes in the denominator of that h?
100.
Okay, now give me the other side of that.
16 over 80.
There you go. That's the way to do it. Now, I can immediately get rid of that and get rid of that. And then I can multiply by 10 to give me that. And now 8 goes into 160 20 times. H equals 20. That's the height of that telephone pole. Okay? All right, on to the next page.
Yeah, number 13.
Now, what is different with this file you sent me? What kind of file is this?
I think I'm not sure.
It's a JPG file. Yesterday, a student sent me a JPG file, and I was unable to blow it up without it rotating. And I couldn't figure out why, and my computer's been doing that for about 3 months. And today is the first time that I've noticed. It seems like I've been able to do this with these files of yours for a while, though, where I could just keep blowing them up and I didn't have to worry about them flipping. I can't do that with most JPG files. They flip on me. I don't know the reason why, but if you happen to be a computer tech wizard, maybe you could set me straight as to why it's working now and it doesn't work the same on all JPG files. JPEG. Those are the most common. That's what all your cell phone cameras take and everything. All right.
Yep.
Let's see. CD bisects ACB. So let me write on here what that tells us right away. Oh, these are good ones, because these are always rotated, and strangely. Okay. AC is 6. That's on there already. Or, excuse me. AC is 8. BC is 6. BD is 5. Find AD. Well, they don't tell you. And without this knowledge, you can't solve the problem. Oh, wow. And that knowledge is that because CD bisects that angle, it's only true if this is a right angle. ACB is a right triangle. If ACB is a right triangle, in other words, if angle C is a 90-degree angle, then the bisector of that creates another right triangle. In fact, creates two right triangles that are similar. You can see why they're similar. In other words, they have two angles that are equal, right? And therefore, the third angle has to be equal. That angle is equal to that angle. Now, again, on problems like this, it is not a bad idea to draw two separate triangles off to the right. One being ACD oriented properly, and the other being BCD oriented properly. I'm going to do it just to demonstrate. Okay? I'm going to draw this triangle. This is D. And this would be A. And this would be, or not A, D. D, A, C. Okay, and now below it, I'm going to draw the slightly smaller triangle. And I know that C got to be there. And D is still the right angle, and B is that angle. And that makes A equal to B, right? So I've got it drawn properly. And now it's easier to see. I know that that's 5. BC is 6. AC is 8. Now I have everything I need because they're similar triangles. So AD, we're trying to find X. AD. Give me an equation.
X over 5 equals 8 over 6.
Correct. So X equal 40 over 6 or 20 over 3. Now, I'm not saying that you need to do this when you take it as a test, because some people are able to see this. You can certainly see that the hypotenuses are 8 and 6, because the hypotenuse is always opposite the right angle. So I know the hypotenuse, but I wouldn't right off the get-go. In other words, if I was going big to little, I could start off by saying 8 is to 6. But now I get a little confused when I look at AD. Is that similar to that side or that side? And in my mind, it's not that easy to see. When I draw them separately like this and label everything, then I can't make a mistake.
Mm-hmm.
But if you try to derive everything from that picture, you might get it correct. Some people have that ability. I'm just not sure I'm one of them. In other words, to kind of rotate it in your mind. The key thing is because it bisects it, we know that that's equal to that. The information they left off was the angle C is equal to 90 degrees. That's absolutely important, because if it isn't, then these two triangles aren't similar.
Mm-hmm.
This rule where you start with a right triangle, bisect the right angle, you actually create 3 similar triangles. You've got that triangle, you got that triangle, and you got the whole triangle. And guess what? They're all 3 similar. That's one of the amazing things happens when you start with a right triangle and you bisect the right angle. You create 3 similar right triangles. So that information is necessary. In other words, we can't figure out what AD is unless we know that is a right angle. And they didn't tell us that.
Mm-hmm.
So we'll go on to the next one. What's the next problem you need to do?
14.
14? Okay.
Yeah, just the next one.
Are these 2 triangles similar? What's your sense?
I think they are, because they have the 2.
What kind of angle is that right there?
More than 90.
Acute or obtuse?
That's obtuse.
Is there an obtuse angle in the triangle on the left?
No.
No. So they're not similar.
So they're not similar.
No, they're definitely not similar. So now how do we figure out the answer? I have a sense, wow, that it's the same problem as this. And they've neglected to tell us that that is a right angle.
Yeah.
And in fact, it almost certainly has to be that.
Or else we can't figure out the problem.
Yeah, you can't figure out the problem otherwise. Or could you? If they're not similar and they're not congruent, I can't imagine we can figure out the problem. If they are, in other words, if that is a right, the big triangle is a right triangle, then we can figure out the problem the same way we figured this one out. And in both cases, we had to assume that that was a right angle. And in this case, I would have to assume that that is a right angle, which means it's not drawn to scale, because if that is a right angle, and clearly that line bisects it because there's two equal angles there, then that means that is a right angle. In the same way it meant that was a right angle up there. Well, they've drawn both of these figures so that neither one of those are right angles. In other words, they have purposefully drawn them not to scale. Now, let me think here for a second. Is that necessarily true? I'm wondering if this might not be a cleverly disguised problem where we do not assume that that's a right angle and we could still solve it. Question is, how could you possibly solve it? We do know that that side's equal to itself. And we know we have one equal angle. But we certainly don't know that angle is equal to that angle, or that that angle is equal to that angle. So I don't see us being able to solve this unless we make the same assumption.
Mm-hmm.
We've got angle, side, side, and we got angle, let me have to think about this one. And I don't want to spend a whole lot of energy on it because I'm pretty convinced your teacher made a mistake and just didn't give you all the information.
Mm-hmm.
In the same way that he or she didn't give it all to you on 13 either. But at least on 13, it looks right. In other words, that looks like a right angle. And I do know that the rule is if that's a right angle and you bisect it, you create three similar triangles, so that would have to be a right angle also. I don't know how to solve 14 if we do not assume that that is a right angle. So what's the next one? I mean, I'm not sure it's worth going through solving it, assuming it's a right angle. We've already done it once this way. We might be wrong because that might not be a right angle. You're not actually supposed to assume stuff that is not given. If they don't give stuff, then you are not to assume it. You're working with nothing but right triangles right now?
No, we have all triangles.
You are, okay.
Equilateral.
These do not have to be right triangles.
No.
Again, I don't know how we could solve this one if that's not a right angle. And let me look at both of these. Maybe I can come up with something, and if I do, I'll mention it tomorrow. I have a session tomorrow. What's after 14?
15.
Okay, I'm going to have to be careful tonight, too. I got to keep my eye on the clock. I have a 5 o'clock, so. Okay, hold on a second. The scale model of the Titanic is 18.5 inches long. The scale is, what's the linear scale factor?
1 to 570.
Yeah, does your teacher always do small to big?
No, I actually don't know.
Here's why big to small works better, okay? If I say 1 is to 570 as 18.5 is to x, that'll give me how long the Titanic is, right?
Mm-hmm.
Notice that that's going to give me a number less than 1. Hold on a second. What the heck am I thinking? No, it's not. It's going to give me x equals 18.5 times 570.
So it's 10,545 inches, I think.
Yeah. Let's see if I do it big to little, it matters. Oh, I know what's happening here. Yeah. See, I would rarely do 1 is to 570. I would do 18.5 is the Titanic, and I know the scale factor is 570. So the real Titanic has to be 570 times bigger than that. Same equation. Not sure what I was thinking, but I know that in a lot of these, I know what I'm thinking is when you're looking at linear scale factors, you'll get to a point in geometry where they'll say, what is the area scale factor? In other words, if I have a square over here that is 1 dimension, and I have a square over here that's 2, what's the linear scale factor between those two squares?
2.
Well, to me, it's 2 to 1. Okay? But if you're I had a geometry teacher once that insisted everybody go small to little, so the linear scale factor was 1/2. Now, what's the area scale factor?
1 to 4.
4 to 1. Notice that to get 1 to 4, you have to square that. You have to square the linear scale factor. And most people know how to square that, but not everybody is going to come up with that. Whereas if you start out with 2 to 1 as the linear scale factor, and now I'm squaring that to get the area scale factor, I cannot make a mistake. The area scale factor is 4 to 1. And the cubic scale factor, the volume scale factor, is 8 to 1. In other words, the area of that is 4, the area of that is 1, and if I draw a third one like that, the cubic one with a side of 2, well, the volume of that is 8, the volume of this is still 1. So the cubic scale factor is 8 to 1, the area scale factor is 2 to 1, or 4 to 1 rather, and the linear scale factor is 2 to 1. And it makes it a lot easier to work with numbers. When you're squaring and cubing numbers, it's so much easier to work with numbers that are greater than 1 rather than less than 1. And if you go small to little, you'll always be working with numbers less than 1. So I suppose that's why I like students to go big to little. It's not so much on these problems here as much as on the problems you're going to encounter soon. 15, the last one on this page?
No, there's 16, I think.
Okay. Still thinking of that first triangle they gave you where they didn't tell you that that was a midpoint line. Your teacher has a habit. Well, we didn't need to know on that one that it was a midpoint line. We were still able to solve the problem. Just turned out that it was a midpoint line. So I can't say that he neglected to give us that information. He didn't need to. But on 13 and 14, it does appear that he's neglecting to give us some information that we need to solve the problem. All right. 16. All 4 vertical lines are parallel. Now let's add some numbers here. Hold on. That's 2. That's 8. 5. M here to here is 6. Obviously, the figure is not drawn to scale, or I labeled it wrong. Right?
Yeah.
FH is clearly shorter than EM. And yet, according to these numbers, FH is 10, and EM is 6. That's okay. It's becoming obvious to me that he purposefully draws these figures not to scale. And that's fine. You're not supposed to figure out the answer based on what it looks like. You're supposed to figure it out based on the algebra involved. Okay. Now, all of these trapezoid A, B, and C, are similar. Because all those lines are parallel. We've got a bunch of similar angles.
Mm-hmm.
In other words, that one is the same as that one, which makes that one the same as that one. That one's the same as that one. So we have similar trapezoids, A, B, and C. So we need to find out EO and EK. And because they're similar trapezoids, what can we say about what can we say? See if you can come up with an equation. For EO. Let's figure out EO and let's start with it. And let's put it in the numerator. EO is to what? As what is to what?
Is to FG.
EO is to 6. We know that measurement. As we know some measurements up here. What goes in the numerator?
FG.
2. Yes, FG. What goes in the denominator?
Is to 15.
2 plus 8.
Oh, 10. 10.
So that's
Yeah, 5.
the only one you have to solve. So EO equals 12/10, which is 6/5. So this dimension is 6/5. And now, what's the best way to figure out the rest of it? How about EK is to what?
EK is to FJ. EA is to 15.
Well, let's do EK is to 15. And I know EK is the smaller one. As what is to what?
As M.
How about EM versus FH? EM is 6. Its corresponding side is FH, which is 10. So here's what we have. Now, let's solve it and see if it makes sense. Is EK going to be smaller or bigger than 15?
EK is going to be smaller.
Yes. In other words, 6 is less than 10, so EK has to be less than 15. And if you do the math, you get EK equals 15 times 6 divided by 10, that's 9. So EK is 9, EM is 6, that's got to be 3. Now, let's just change that 6 to 4 and 4/5. See where I got that? In other words, EM is 6. So now I have the dimensions of all 3 pieces. And I have the dimensions of all 3 top pieces. So it's really clear that the longer line is FJ. But we knew that already by 5/3, or by 10 versus 6. That established the ratio. 10 was to 6. Or 6 is to 10. In this case, it actually does make more sense to go little to big. 6 is to 10. But I solved the problem by always starting with the thing we're trying to solve, EK. I start with that way it'll be in the numerator for sure. And I know the total distance of that is 15, so I'm going to say EK is the 15 versus the smaller piece to a bigger piece that are known. All right. See if we can get in another one here. What's the next one you have to do?
Number 20, which is
okay. These tend to have some hard ones on here. I know they did last time. When we were talking about scalene quadrilaterals and stuff.
Yeah.
Hold on, something didn't work right here. All right. 2 isosceles triangles are similar if a base angle of one is congruent to a base angle of the other.
That would be.
If you get it right, we don't need to talk about it. We'll go to the next one.
That's always true.
Number 2, 2 isosceles triangles are similar if the vertex angle of one is congruent to the vertex angle of the other.
That is also always true.
An equilateral triangle is similar to a scalene triangle.
That is never true.
2 sides of one triangle are proportional to 2 sides of another triangle. The triangles are similar.
That is similar.
Well, let's draw a triangle like that. 2 sides of a triangle are proportional to 2 sides of another triangle. Now, the other triangle I'm going to make bigger so that the horizontal lines are proportional to the other lines. So, there's only one way I can draw the third side of that. That makes them similar. No, it doesn't. I can draw this 2 ways. In fact, I'll go ahead and draw it so they're almost congruent. Side 1 is the same as side 2. Excuse me, side 1 prime, and side 2 is the same as that side 2. And yet those triangles are neither congruent nor are they similar. That is also why side-side angle does not prove congruency. Notice that that angle is the same as that angle. So I definitely have side-side angle, and yet I do not have either congruent triangles or similar triangles.
Mm-hmm.
So sometimes, and obviously in this case up here they are. So there are cases where they are similar, but if I can draw one that's not similar, then it's not always and it's not never. So it has to be in between sometimes.
Mm-hmm.
Okay. I think that's probably a good place to stop. Let's just take a quick look at this one. It's starting to get hard. A, C. Got a feeling this is going to point out what I just pointed out. A is 40. AB is 6. Yeah, it is. BC is 8. And then you have triangle RST, where RS is 12, ST is 16, and angle R is 80. Are these similar or congruent?
No. So it's never.
No, 80 is not the same as 40. Now, I suppose that there might be a 40-degree angle over here. The only reason I'm not totally comfortable with that answer is of what if that's the 40-degree angle? And now this is 80 and 60. And over here we have 40, 80, and 60. So we could have similar triangles if angle A, but I think almost by definition, if you make this statement right there, you are saying angle A is the same as angle R, correct?
Mm-hmm. Yes.
They are never similar. In other words, what I was doing over here is possible. I could draw another triangle that would have a 40, a 60, and an 80 in it, and it would be similar. But it wouldn't be called this. I wouldn't be able to say triangle ABC is similar to triangle RST. Sorry, I forgot about my other session. Gotta go.
Yep. Bye.
Bye-bye. I'll talk to you tomorrow. Maybe I'll have an answer for those other two.
Okay.
All right. Bye-bye.